2015 Physics Group Project. Phenomenons of Water Pressure.
Proudly presented by Rixon, Azin, Licheng, Jianfu, Brandon Tan.
Our project is titled Anti-Gravity Bottle. For our experiment, we use a plastic bottle filled with water. The bottle has been sealed with cling wrap. Notice that the water doesn't leak out, as all of us would have expected. Now, we are going to poke a toothpick into the cling film. The toothpick rose and floated on the surface of water. Let's look at the replay for a clearer view. Why did this happen? When toothpick is fully immersed into the water, given pressure equals to H rho g, the pressure at the top end of toothpick P1 equals to H1 rho f g. Hence, the force exerted by water on top end of toothpick F1 equals to P1A equals to H1 rho f g A. Similarly, the pressure at the bottom end of the toothpick P2 equals to H2 rho f g, and force exerted by water on bottom end of toothpick F2 equals to P2A equals to H2 rho f g A. As H2 is more than H1, the upward force F2 is greater than the downward force F1. This net upward force is called upthrust. Upthrust is the upward force exerted by a fluid on a submerged or floating object. It arises due to the difference in pressure between the upper and lower surface of the object. By Archimedes' principle, upthrust experienced by the object is equal to the weight of water displaced. This can be explained using this proof. Upthrust exerted by fluid on toothpick U equals to F2 minus F1 equals to H2 rho FGA minus H1 rho 1GA equals to H2 minus H1 rho FGA equals to H rho FGA equals to VF rho FG.
Now, let us consider the free body diagram of a toothpick. The two forces acting on the toothpick are the upthrust and weight of toothpick. We denote the upthrust by U, where U equal to Vf rho f g. Given Vf equal to volume of fluid displaced, rho f equal to density of fluid, and g equal to gravitational acceleration. The weight of the toothpick is given by W equal to mg equal to rho t Vt g, where rho t is density of toothpick and Vt is volume of toothpick. Thus, resultant force acting on the toothpick is given by summation F equal to U minus W equal to Vf rho f g minus rho t Vt g. Since volume of fluid displaced is same as volume of toothpick, therefore rho f equal to Vfg bracket rho f minus rho t. Since the density of water is much greater than density of toothpick, there will be an upthrust resultant force on the toothpick, causing toothpick to rise upwards to the top of the fluid. By the principle of flotation, the toothpick will float in equilibrium when upthrust is equal to the weight of the object. This is when the toothpick remains at the top afterwards. Now that we have understood why the toothpick floats up, we will look into the question that stumbles many. Why does the water not leak out even when there are many holes after the toothpick has poked through the cling wrap?
Now that the bottle is being tilted, the water will now exert a weight on the cling film since it's touching the cling film. In order to counter the weight that's being exerted by the water, the cling film will have to exert a reaction force opposite to that direction of the weight of the water, such that the water does not leak out. Such that now we know that by the Newton's second law, since the system is in equilibrium, the resultant force of the system will be equal to zero. The reaction force that's being exerted by the cling film on the water will minus of the weight of the water and be equals to zero as well. Rearranging the equation, we know the reaction force exerted by the cling film on the water will be equals to the weight of the water. Now we know that the cling film exerts a reaction force upwards. Hence, the reaction force upwards exerted by the cling film will be exerted over a surface area. The surface area will be the area of the hole. As a result, the pressure will be exerted by the cling film onto the water. We know that the pressure that's being exerted by the cling film over the area onto the water will be given by R over A to the subscript of H. A to the subscript of H will be the area of the hole, and R will be the reaction force that is being exerted by the cling film onto the water. From the previous equation, we know that R equals to the weight of the water. And the weight of the water, as we continue to expand further, we know that the weight of the water will be the mass of the water times the gravitational acceleration of the water, whereby R equals to mg. Hence, the pressure that's being exerted by the cling film will be given by the weight of R over A to the power of subscript of H, and it is actually equals to the weight of the water over the area to the subscript of H. So it's actually finally equals to mg over A to the subscript of H. Now we'll hold on, and now we'll see. This will be our first equation. Our second equation aims to prove the pressure of the water that's being exerted onto the hole of the cling film. Now we see that above the hole there is a column of water, and the column of water has a certain height. The pressure of the water that's being exerted onto the hole will be given by x plus y to the subscript of n multiplied by rho, which is the density of the water, and then multiplied by g, which will be the gravitational acceleration. As we know by theory that there is a column of water that is being above the hole, and hence we need to find the pressure of the water that is being exerted onto the hole. So we know that the density of the water is being given by the mass of the water over the volume of the water. We now sub this expression into the equation. So now we will get x plus y to the subscript of n multiplied by m, which is the mass of the water, g with the gravitational acceleration, then over v. Now we also know that the volume of the water is actually equals to the area of the hole multiplied by the whole height of the water above the hole, which will be given by A to the subscript of H multiplied by x plus y to the subscript of n, which will be the height of the water. Now, as we sub in this expression, our new equation will be x plus y to the subscript of n multiplied by m multiplied by g, which is gravitational acceleration, over A to the subscript of H, which is the area of the hole, multiplied by x plus y to the subscript of n, which will be the height of the water above the hole. As we continue to simplify the equation, we will get mass of the water multiplied by g, which is gravitational acceleration, over A to the subscript of H, which is the area of the hole. From this, we know that the pressure of the water exerted onto the hole will be given by mg over A to the power of H. For the previous equation, we know that the pressure of the cling film is being exerted on the water will be given by mg over the A to the power to the subscript of H. Hence, we know that actually the pressure that the cling film exerts on the water is equal to the pressure the water exerts on the cling film. As a result, there is no resultant change in the pressure, and the resultant pressure change in the system is actually zero. The new pressure minus the initial pressure will be given by the new pressure of the air minus the initial pressure of the air in the system plus the new pressure of the water over the initial pressure of the water in the system. We know that for this, there's no resultant change of pressure in that of air. And now we look at that of water. We know that there's also no change in the pressure of the water. Although there's an increase in the pressure of the water for the new, it is being minus off. It is being cancelled out by the pressure that is being exerted onto the water by the cling film. As a result, the final pressure change still accounts to be zero. Now we know that since there's no change in the pressure of the final system and the initial system, the pressure of the final system minus the pressure of the initial system will be equal to zero. Hence, the pressure of the final system is equal to the pressure of the initial system. Since we know that in order for the system to remain in equilibrium, we know that the pressure of the pressure of the initial system must be equal to the pressure of the atmosphere. Since we know that the pressure of the final system is equal to the pressure of the initial system, and the pressure of the initial system equals to the pressure of the atmosphere, we know the pressure of the final system is also equal to the pressure of the atmosphere. Since there is a balance of pressure, the water will thus not leak out.
Physics is cool and beautiful. It is crazy too. From the previous part, we made an anti-gravity bottle. Now, we will make another interesting phenomenon that dwells in water, the amazing fluid which physicists and chemists are crazy about. Well, anyway, observe that when we swipe the water streams stick together, and then it separates again. In the chemical structure of water, oxygen is bonded to hydrogen and oxygen has lone pairs. The high electronegativity of oxygen will attract the shared pair of electrons closer to it, inducing a positive partial charge on hydrogen. When you move your finger across them, you allow these bonds to form between the multiple molecules of each stream, creating interstream cohesion. This causes water to act as a continuous string, as the preceding water molecules will hence be at a close range to adhere with hydrogen bonds.